We can visualize our examples represented by feature vectors as points in space. It's easiest to do that in a two-dimensional space, a plane, or even in a three-dimensional space. But keep in mind that most of our feature vectors are high-dimensional. The two- or three-dimensional exercise is still helpful to understand intuitively what's going on. So we have these examples scattered in a plane or 3D space. Some of these examples belong to the positive class and some of them belong to the negative class. We are trying to find a decision boundary. We are trying to put a fence between the positive examples and the negative ones so that we can predict everything on one side as positive and everything on the other side negative. So the weight vector represents this decision boundary. In the general case, this decision boundary is a hyperplane. In a two-dimensional place, the decision boundary is a line. In a three-dimensional space, the decision boundary is a plane. The dimensionality here depends on the number of features. With two features, we have a plane and a line as the decision boundary. With three features, we have 3D space and a plane as the decision boundary, and so on. Let's go back to our spam example and consider only two features: the number of times the word free appears in the email and the number of times the word money appears in the email. Here is our weight vector. Of course, it also includes a bias. So our decision boundary here is a line. This is the line where the dot product is 0. So everything on this side of the line will classify as spam. The dot product is positive on this side, and everything on this side of the line will be classified as ham. The dot product is negative on this side. So that's basically how the weight vector corresponds to the decision boundary between the two classes. There are two perceptron-related tasks involved here. We have a classification task. How do we predict the label based on the features and the weight vector? We have seen how to do that by computing the dot product. And we also have a learning task. How do we learn the weight vector from our training data? Let's see how to do that next. The main idea here is that we're going to learn from mistakes. We'll start with some arbitrary weight vector. We look at one training example at a time. We classify this example with our current weight vector. If our prediction is correct, we do a happy dance and move on to the next example. If our prediction is not correct, we update the weights. We move our decision boundary so that our prediction is less wrong. So here's the binary perceptron learning algorithm. We start with weights all zeros, and then we look at one training example at a time, and we classify with the current weights. We just compute the dot product, and based on whether this dot product is positive or negative, we classify with the positive class or the negative class. So let's say we guess the label Y. Now remember, this is a training example. It came with a training label. Somebody labeled this example and told us the right answer. So let's assume this answer, this correct answer is Y star. We compare our guess to the correct label. And if they match, if Y is equal Y star, that means we predicted correctly. We don't need to change anything. We do a happy dance and we move on to the next training example. Now, if we guessed wrong, if we predicted a different class than the one that came with that example, we have to adjust the weight vector. We have to push the boundary so that that example falls into the right region. And we repeat this process until there's no more significant changes. So we perform several iterations here. Here's the algorithm flushed out. We start with weight 0. We classify with the current weights, and we know how to do that based on the dot product. If our prediction is correct, there's no change needed. We do our happy dance and move on. If our prediction is wrong, we need to adjust the weight vector. We do that by adding or subtracting the feature vector from the weight vector. So let's take a look at this feature vector. The dot product of f and w here is positive, so our prediction is the positive class. But let's say that this example came with a negative label, so we should have predicted negative. So we subtract f from w to move our boundary so that f is in the negative region. So if y is negative, we end up subtracting f from w, and that kind of pushes f into the negative region. Now, if we predicted negative and the label was positive, we add the feature vector to the weight vector. So this works well when the data is separable. Let's say I have these examples here. I look at each one at a time. And let's say I start with this positive example that is right here. So my current weights put my decision boundary here. And I predict positive with my current weight, so that's fine. I don't do any weight updates here. Let's then say I look at this negative example here. With the current weight vector, this negative example is classified incorrectly. It's going to be classified as positive. So that's not right. I need to update my weight. So I push my boundary. Now I may overshoot and push my boundary all the way over here. That's fine. I move on to the next training example. So let's say I consider this positive example now. Now, if I were to classify with this boundary, this positive example is going to be classified as negative, and it's positive. So I made a mistake here. I need to adjust for my mistake. I need to update the weights, and I push the boundary down so that this example is classified as positive. And we keep on doing that. So let's say I consider this negative example next. Now I have to push my boundary up to correct for it. And here, now I consider this example, and this example is going to cause me to push my boundary here. At this point, all the examples are going to be classified correctly, and I have no more weight updates. So in this case, I was able to separate the data. So there's this notion of separable data. So data is separable if there are some parameters that get the training set perfectly correct. Unfortunately, not all data is separable. So we may have data like this. Here there's a negative example here in the middle of the positives, and there's a positive example here in the middle of all the negatives. So this may be due to noise in the data. This may be due to labeling mistakes. There is no way we can find a boundary here, a linear boundary that would divide this plane into two regions where we have positive data on one side and negative data on the other side. So with the perceptron, we have a guarantee of convergence, but only if the training data is separable. So if the training data is separable, the binary perceptron rule is guaranteed to converge. Here's a visualization of weight updates with non-separable data. So here we have a positive example in the negative region, basically. So there's no way we can separate these examples into positive and negative and get them all right. So what happens is our perceptron keeps updating the weights, and we keep thrashing back and forth, and there is no convergence. We'll see how to deal with non-separable data in the next lecture.